Let's take a look at finding the derivative of a quadratic equation here, 3x minus 2x squared, using the limit definition. And I'm looking for the derivative function f prime of x, so not the derivative at a point, but really the derivative everywhere, for any x value you could care about. And the setup for this is it's the limit of the difference quotient, f of x plus h minus f of x all over h. Although it might not look like it, this is y2 minus y1 over x2 minus x1. It's the slope of a line. If you were to subtract x plus h and x, the x's would cancel, leaving you with just the h there. So this is the change in your y values over the change in your x values as you get closer and closer to a given value x. Now, in order to do this, I need to know what f of x is for my function, but that's just our function. It's already labeled as f of x, and f of x plus h. And f of x plus h means plug x plus h in for your input, everywhere where you used to have an x. So if I wanted to rewrite this, I'm going to have to limit as h goes to 0 of f of x plus h. This is this 3 times x plus h minus 2 times x plus h squared minus f of x. And notice I'm putting f of x plus h and f of x into parentheses or brackets. They work the same way, however you want to write them. But I need to make sure that I'm careful with the signs. I'm subtracting all of f of x. So I'm subtracting 3x, and I'm subtracting a negative 2x squared. I'm going to be careful with my sign. This is all over h. I'm going to make some things worse before I make them better. I'm going to multiply this 3 out here. So distributing the 3, that gives me a 3x and a 3h minus 2 times, and I'm going to multiply out that x plus h squared. If you were to write that as x plus h times x plus h, x times x gives you x squared, x times h gives you hx, h times x, I'm foiling, gives you hx, and h times h gives you h squared. So combining like terms, if I were to multiply that out, I have x squared plus 2xh, or 2hx, however you want to write it, plus h squared. That still needs to get hit by that negative 2, so that's why I'm keeping this in parentheses. Minus 3x minus 2x squared, whew, all over h. Let's multiply that negative 2 out, distribute it to each of those pieces. So I've got 3x plus 3h minus 2 times x squared, so minus 2x squared, minus 2 times positive 2xh, that gives me minus 4xh, minus 2 times h squared, that's minus 2h squared, minus 3x minus 2x squared all over h. And now is where we can start to cancel some things out. Because I have a 3x minus a 3x, those are going to cancel. I have a minus 2x squared and a minus 2x squared, those are going to cancel. So the things I have left on the top, 3h, minus 4xh, and this minus 2h squared. All of these pieces have h. Let's write what's left over. And then let's simplify further by dividing each of these components by h. 3h over h becomes 3. The h's cancel, because they all have this h. I'm dividing that h out. H's cancel in the center. That leaves me with 4x. one of the h's cancel here at the end. So you used to have h squared. I still have one h left. So that's 2h to the first power, or just 2h. As h goes to 0, I'm going to plug 0 in for h. That gives me 2 times 0, or 0. So I have 3 minus 4x minus 0, or 3 minus 4x. So if I were to look at the derivative of my starting function, that starting function again was 3x minus 2x squared. It should leave you with 3 minus 4x as the derivative function. If you know the power rule, you could prove this using the power rule, but this is what it looks like using that limit definition. In general, when you're working with that limit definition, things are going to get messier when you expand it out, and then it'll get a lot cleaner as you combine your like terms. That's always kind of the main setup for these problems, is I'm trying to make it look as nice as possible by simplifying everything that I possibly can. Let's take another look at an example of something like this.